In our last lesson, we learned about ionic bonding, which is between a metal and a nonmetal. So remember, the metal loses electrons, the nonmetal gains electrons, then you have a positive and negative charge that's attracted. So with metallic bonding, you may think that it's impossible for two metals to stick together because they would both be positive and two positives would repel. But they actually don't. There's a way that you can get them to stick together. So first of all, metallic bond is between two metal atoms. And the reason they stick together is because their electrons are so loosely held, like metals just want to get rid of those electrons, so you end up with this big blanket of electrons that's surrounding the positive nuclei, and that blanket of electrons holds all the metal atoms together. So like if you have a silver ring on your finger, the reason those silver atoms are not splitting apart is because it has this blanket of electrons that's holding them together. And in chemistry they call it a sea of electrons. So in your notes you need to highlight that phrase or circle it or put a box around it. Sea of electrons you need to associate with metallic bonding. And this is kind of a picture you can see. These little electrons here are just kind of floating from atom to atom. So each electron has lost a few atoms, which is why they're positively charged. So these are all aluminum atoms. And this blanket of electrons just kind of flows in and out just like this. And it just holds all those aluminum atoms together. So the metallic bond, the actual definition is the attraction of those free-flowing electrons for the positively charged metal ions. And again, it makes a crystal structure. So we talked about crystal is just a repeating pattern. Both ionic and metallic bonds do that. And the reason that metals have all the properties that they have is because of these free-flowing electrons. So if you can remember from our last chapter, we talked about metals are malleable, which means they dent when you hammer them. The reason they dent is that if you hammered this aluminum right here, all these little electrons would just slide out of the way, and so you don't end up crumbling it. They just kind of move to the side, and it just dents it. Same thing with good conductors. We talked about metals are good conductors, and that's because electricity can just flow right through all these little electrons here, and that allows it to conduct electricity well. So just to review, the reason that metals have all of these properties, and you memorized these last chapter, so they should be familiar to you. The reason they have these properties is because of those free-flowing electrons. So just to review, there's two ways now that we talked about metals can bond. They can form an ionic bond if they stick to a nonmetal, and so that's when you have a transfer of electrons. They can also form a metallic bond with other metals if they get that sea of electrons that holds them all together. And the only type of bond we haven't talked about then is if you have two nonmetals together. And you may think that two nonmetals would not stick because they would both be negative. Nonmetals always want to gain electrons. But instead of gaining electrons, they can also share them. So a covalent bond happens when two nonmetals are going to share their electrons to make sure that they all get those 8 octet in their octet. And it occurs between two nonmetals. So again, this time they're sharing electrons. So just to separate the two, yesterday we talked about ionic bonds where electrons are transferred, so the key word is transfer. Today we're talking about covalent bonds where the electrons are shared. And keep in mind that hydrogen will always form a covalent bond. Some people get confused by hydrogen because it's on the metal side of the periodic table, but remember hydrogen is just a really weird element, so it actually acts more like a nonmetal than a metal, even though it's to the left of the staircase. So keep in mind that hydrogen will always make a covalent bond. And covalent compound or molecular compound just means it's held together by covalent bonds. So here's a picture because I've said before, pictures help me better than words. What we did in our last lesson is on this side, on the right. So notice that this electron got transferred over to this atom, which means that this atom is now positively charged and this atom is now negatively charged. So we have two oppositely charged ions that are going to be attracted. So the key word here is transfer. Covalent is what we're doing today. So instead of transferring it, notice that they're both sharing it. So these two electrons can now float around either atom, which means they're sharing it, and that makes it more stable. So ionic is transfer, covalent is sharing. For a covalent compound, the smallest unit is called a molecule. which is different from ionic. So just to review, ionic, we talked about the smallest unit is called a formula unit, and it doesn't actually exist as an independent unit, even though it has the word unit in it. It's very confusing, but it's actually a ratio. So when you see the word formula unit, you need to think ionic and ratio. It's a ratio of ions. A molecule can exist by itself. So it can exist as an independent unit, kind of like when you have water, which is H2O. You have 2 hydrogens and 1 oxygen, so 3 little atoms, and they're stuck together and they float around like a little family of 3. Formula units don't do that. Formula units are just ratios between the ions. A diatomic molecule sounds fancy, but you can just figure out what it is if you break apart the word. Di means 2, which you should probably figure out, and then atomic just means atoms. So it's a molecule that consists of 2 of the same type of atom. And there's 7 elements on the periodic table that when they're in nature all by themselves, they're always more stable if they pair up together. And these are the 7 elements that you'll need to memorize. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those 7 elements, if they're by themselves, it's more stable for them to stick to another partner. Now, it doesn't take into consideration compounds. So like if you put sodium with chlorine, chlorine wouldn't necessarily have that 2 on there. The only time you put this 2 on there is if it's by itself. And there's 2 ways you can memorize it. First of all, if you know that there's 7, just go to the periodic table and start with element 7, which is nitrogen. And if you go over to fluorine and down to iodine, it makes a 7 on the periodic table. So start with nitrogen, go straight across to fluorine, and straight down to iodine. And that includes all of them except for hydrogen. So you just need to remember hydrogen is also diatomic. Or you can just say the word Hofbrinkel, and anytime I say you forgot about Hofbrinkel, what I'm saying is you forgot to put that little 2 on there. The only thing with that is you have to make sure you know what those sounds mean. So if you think the coal part of that is like carbon and lithium, then you're going to get it wrong. So just make sure you understand those. And what you can do is just list Hofbrinkel across the top of your test or quiz whenever you take one, just to remind yourself that those 7 elements get a little 2. Molecular formula is pretty much the same thing as ionic formula, except it's not a ratio, it's the actual compound itself. So it shows you how many atoms of each type of element you have. But keep in mind that it's not a ratio this time, so you don't have to simplify it. For example, C6H12O6 you may recognize as a type of sugar from biology. You had to do this with photosynthesis. You could simplify this to CH2O, but since it's a molecule, you don't simplify it. So what this says is that you actually have all 24 of those atoms that float around together as a unit. So to do these, what you're going to do is put some dots around it, and you're going to show how the dots are being shared, and then you draw lines to show the bonds. And this is not something that I can explain over a video. I have to actually draw it and show you how to do it. So if you're watching this because you missed class, just come on in and see me at lunch, and I can show you how to do these dots and draw the pictures. If you were in class and you're just watching this for a review, you can look at your notes and your worksheets to see the kind of pictures that we drew for these. Anytime you have those pictures that have electrons that are not part of a bond, we call those unshared pairs, lone pairs, or non-bonding pairs. I don't know why they have 3 different things for it, but that's just what scientists use. So it's a pair of valence electrons that's not being shared. And these examples are a little bit more complicated than the first examples because they involve double and triple bonds. So it's sharing more than 1 pair of electrons. And again, it's not something that I can explain over the video, so just come in at lunch and see me and I can show you how to do these. A single bond is when atoms share 1 pair of electrons, so there's only 2 electrons total that are being shared. This is the longest, the weakest, and there's less energy involved in this. Double bond shares 2 pairs of electrons, so that's a total of 4 electrons. And a triple bond shares 3 pairs, so that's a total of 6 electrons. And the more bonds you have, the closer the atoms get to each other, and the stronger the bond is going to be. So for bond length, it's the shortest for triple bonds, and for bond strength, it's the strongest for triple bonds. And the way I think about it is just if you have two things held together by a rubber band, if you put one rubber band, it's going to be kind of long and not very strong. But if you add a second rubber band, it would pull them together even more, so they get shorter and stronger. And if you add a third rubber band, it would get even shorter and stronger. So that's how I remember it. We've already talked about a few exceptions to the octet rule. We talked about hydrogen and helium only need 2 electrons. But keep in mind that helium, since it's already stable, you'll never draw pictures with helium in terms of the molecules because it's never going to form a molecule. Helium's already stable, so it's not going to ever bond up with anybody. Boron and beryllium are 2 that we have not talked about yet. So beryllium, instead of needing 8 valence electrons, it's only going to need 4. And boron only needs 6. So put a star by those and make sure you memorize that hydrogen needs 2, beryllium is 4, and boron is 6. And the last thing for today are just the properties of covalent compounds. And what's in red is what you should memorize. The good news is they're pretty much the opposite of ionic. So if you know what ionic compounds are, just flip around the properties and now you have covalent. So there tend to be weaker bonds, liquids or gases, they have low melting points, they do not conduct electricity well, and they're not soluble, which means they can't really dissolve in water, as well as ionic compounds. So now we've covered ionic, metallic, and covalent compounds, and it's important that you understand the differences between those 3 bonds. So make sure you study those hard before our next lesson. And that's it for today.